We had a total of 6 questions to do over the weekend for homework, and we want to go over 3 of those questions now from page 215, number 2, number 5, and number 6. Number 2 says, describe how a torsion balance can be used to measure the gravitational constant G. All right, let's briefly go through that experiment again then. You remember that the word torsion means twisting. So if you remember that, then that's kind of your little hint as to what's going on with this experiment, the torsion balance experiment or the twisting balance experiment. You got an anchor like the ceiling or the top of a box or something. Hanging from that anchor is a string. And on the end of that string, you have a little rod. And on either end of that little rod, you've got a mass. Okay, one of them we'll call mass 1. The other one doesn't really matter. It has to be the same mass so that this thing doesn't literally tip over. Okay, but other than that, it doesn't really matter what it is. Okay, we've got mass 1 on one end. Mass 2 is going to be brought nearby mass 1. We can measure a few different things for this now. R relatively easily. Okay, R is the distance that separates M1 and M2, so we can find its value pretty easily by a ruler or some kind of measuring device like that. We can find the value of M1 really easily just by weighing it on a scale. M2, same deal. Now there's one more variable that we need, however, to find the value of G, and that's force. Okay, if we're going to use the equation, Newton's law of universal gravitation equation, to find the value of G, which is exactly what Cavendish would have done. Okay, taking this equation, rearranged it, F times R squared over M1 times M2, we need the value of F. How do we get the value of F from this experiment? It's like the swing set, right? You're on the swing set, you twist it around so that you can spin around faster and faster and faster. Okay, when you twist it, you know that the more you twist it, the harder it is to twist. Okay, you could, if you wanted to, do an experiment that would measure the amount of force that was required to twist it 45 degrees, to twist it 90 or 180 or 360 all the way around. And then the next time somebody was to twist that swing, you could say, oh, it twisted 37 degrees. It must have been this much force. So you can know the torsional properties of the swing set. You measure how much force is required to twist at a certain value. And then you can go back and say, oh, if it twists this much, then it must be this much force. That's what Cavendish would have done. He would have said, look, if it twists 12 degrees, then it must have been a force of this many newtons. If it twisted 2.4 degrees, then it must have been a force of this much. So he's able to measure the force not by some kind of scale, but rather by looking at how much the string twists when mass 2 is brought near mass 1. Now, it's going to be a really, really small angle, but nevertheless, it's going to twist, right? There's going to be a force, so therefore that string is going to twist. Now that he's got the value of R and M1 and M2 and F, he can put them all into here, and he can calculate the value of G. And he'd probably repeat that a bunch of times, average the values, but in the end, we got the value of G there. That make sense? Who asked me for that one? What was it? Dave, is that okay? Second question we wanted to go over is number 5. This one says, Mars has 2 moons, Deimos and Phobos, each named after an attendant of the Roman war god, Mars. Deimos has a mass of 2.38 times 10 to the 15 kilograms, and the mean distance from Mars is 2.3 times 10 to the 7 meters. My son's in grade 7, and he came home the other day with his math book, and he was doing some homework in math. And the thing that they were doing in math class in grade 7 was, what is it? Mean, mode, and that's a median, mean, median, and mode, right? You guys remember those? What does mean mean? Means the average, right? So the average distance from Mars is this value. Why do we say the average or the mean distance? Because the reality is, we know, according to Kepler's laws, that they're going around not in circles with a constant radius, but they're going around in ellipses with a changing radius. But the average is this value, 2.3 times 10 to the 7. Phobos has this mass, and it's this distance. A says, without doing any calculations, predict which moon will exert a greater gravitational force on Mars, and explain your reasoning. Who's got an answer for that? Okay, David. Why do you think Phobos would exert a greater gravitational force? Good, good. Perfect answer. It has more mass, and it's in the distance separating Mars from that moon is smaller. So as m goes up, that makes the force of gravity bigger. As r goes down, that makes the force of gravity bigger. Now, if m was going up and r was going up, then the effective mass would be the increased gravity, the effective r would be the decreased gravity, and then you'd probably have to crunch the numbers to see which one had the greater effect. Okay, but when m is going up and r is going down, it's unequivocally going to have a stronger force. So you're absolutely right, David. It would be Phobos that would have the bigger force because of bigger m and smaller r. 6, we want to check our predictions by calculating the magnitude of the gravitational force exerted by each moon on Mars. Okay, easy enough here, guys. At this point, we're going to say the force of gravity between Phobos and Mars is gm1 m2 over r squared. That's 6.67 times 10 to the minus 11 times the mass of, let's say, Phobos, 1.1 times 10 to the 16, times the mass of the moon, which is 6.24 times 10 to the 6.42, times 10 to the 23. Divided by the average distance that separates them. What have I just found here? Yeah, Phobos is 9.4 times 10 to the 6 meters. And don't forget to square that number there on the bottom. Let's say this side of the room, Nick's side over. Calculate this one, please. Get that force. And the other side of the room, okay, Fraser and over, you guys are going to get the force of gravity on Deimos. Same equation, gm1 m2 over r squared, but this time our mass is a little bit different, and so is our distance. 6.67 times 10 to the minus 11 times the mass of this planet, or this moon, I should say, 2.38 times 10 to the 15, times the mass 2, which is the mass of the moon again, 6.42 times 10 to the 23. Divided by the distance, 2.3 times 10 to the 7. And again, don't forget to square it. Okay, on this side of the room, who's got the value of the force on Phobos? .3308. We're going to round that actually to probably 2 digits, right? 5.3 times 10 to the 15. Thank you, Stefan. Do you agree with that, guys? Yes, good. Thank you. And somebody on the other side, let's get the force of gravity between Phobos and Mars. You get that one, Jenna? 1.9 times 10 to the 14 newtons. So sure enough, David's prediction that we knew was right, but we've confirmed it mathematically now. We say that, look, the force on Phobos is what, about 30 or 40 times the force on Deimos, which makes sense, right? You're increasing the mass, you're decreasing the distance, force is going to be a lot bigger, and sure enough, it is. Okay, Mouse? And finally, the last question that we wanted to go over, question number 6, it says, suppose the equatorial radius of Earth was the same as the moon. The equatorial radius, that means the distance from the center of the Earth to the equator on Earth. We're saying suppose it's the same as it was on the moon, which it's not. Clearly, the radius of the Earth is a lot bigger than the radius of the moon. The Earth is a bigger planet. But let's pretend that it was for a second. But the Earth's mass remained the same. So we're making it a lot smaller, but we're making it the same mass. We want to know the gravitational force that this hypothetical Earth would exert on a 1.0 kilogram object at its surface. Do you think that it would be smaller or bigger than the actual force of gravity is? Okay, we keep the mass of the Earth the same, but we make it smaller. Do you think that's going to have a bigger effect on the 1 kilogram object or a smaller effect on the 1 kilogram object? Same mass, smaller radius. Got it? I think it's going to have a bigger effect. In fact, I know it's going to have a bigger effect, right? Because what you're doing, and this kind of comes back to what David said a minute ago with the other question, right? If you make R smaller, now we're not increasing mass this time, but we're still making R smaller. You make R smaller, that's going to make force bigger. So let's do that. Let's find that force of gravity now. G m1 m2 over R squared. We get 6.67 times 10 to the minus 11 again, times 5.97 times 10 to the 24 times, I like it when the mass is 1 kilogram, eh? Divided by the distance of, we want the equatorial radius of the moon, right? 1.74 times 10 to the 6. And then we got to square that. Let's do that one together, all right? 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 times 1 divided by bracket 1.74 times 10 to the 6. And we got to square that. Oops. Somebody have the value for there? I just messed up on the calculator. We should have 3.98199 times 10 to the 14 divided by bracket 1.74 times 10 to the 6 squared, not times 2. 131.5. We get that? We're going to round that to 3 digits. So we're going to make it 132. 132 newtons. Now it says in B, how does the answer in part A compare to the actual gravitational force exerted by the Earth on this object? Well, listen carefully to what I'm about to say here, guys, okay? This is something, the first time that we see this, but it's the first of many times that we see this between physics 20 and physics 30. That's the word compare. Whenever you want to compare two things, or whenever you want to find a ratio of two things, you're going to do exactly the same thing. We see this a lot more in physics 30 than we do in physics 20, but we see it here as well. Compare ratio of two things. What are we going to do? Well, let me give you an analogy to help you to understand what's the best way of comparing two things numerically. Okay, let's say you guys are 16, right? Okay, most of you guys are 16. Let's say I'm 48. I'm not even close, but let's assume for a second that I'm 48 and you're 16. If we said, let's compare my age, okay, 48, to your age, how would we do that? What's the best comparison of my age to your age? I'll tell you one way of comparing them is to subtract them, right? I'm 32 years older than you are. Is that a decent comparison? Sure it is. We're comparing my age to your age by saying I'm 32 years older than you, but it's not the best way to compare. Here's why. Let me give you another little analogy here, okay? When you were 1, that would make me 33. Okay? 32 years difference, right? I'm still 32 years older than you. When you're 16 and I'm 48, then still 32 years older, but it seems to be a little bit less of a difference. Okay, we can have a conversation now and understand each other. There's still a lot of things that are different about us when I'm 48 and you're 16, but it's like we're closer now in age. We're not really closer in age, right? We're still 32 years difference, but it seems like we're closer. When you're 100 and I'm 132, then still 32 years difference, but in the end, at that point, we're all just going to be old people complaining of sitting in the same nursing home together, complaining about our families not coming to visit us. There's not going to be really any difference, right? Really. So subtracting isn't the best way to compare, because when I'm 132 and you're 100, it's 32 years difference. When I'm 33 and you were 1, it's still 32 years difference, but it's a big difference, right, between when you were 1 and when you were 100. The best way to compare it is to divide. When we want to compare two numbers or find a ratio between two numbers, we want to divide those two numbers. So let's divide my age by your age. I'm 48. We're pretending, remember, that I'm 48. You're 16. 48 divided by 16 is 3. So the ratio of my age to your age is 3 to 1. Or I'm 3 times the age of you. Why is that better? Well, because when you were 1 and I was 33, the ratio of our ages was 33 to 1. Right? It gives us a better perspective when the numbers change, right? We want to compare this number to the actual gravitational force exerted by the Earth on this object. Let's divide them. Now, there's a couple of ways we can find the force of gravity on the surface of the Earth. And we got this one if the value up here if the radius of the Earth was different. But if the radius of the Earth is what Earth actually has, then we could actually say F is equal to gm1m2 over r squared with the actual Earth numbers. Or this time we could actually say F is equal to m times g, right? Okay, why can we get away with that this time? Well, because the Earth's gravitational field on the surface of the Earth, when the radius is what it's supposed to be, is 9.81. So my weight, or the force of gravity on this 1 kilogram object, when the radius of the Earth is what it's supposed to be, is 9.81 newtons. Now, we want to compare these two, or find the ratio of these two. And what we're going to do is say 132 divided by 9.81 gives me, what does that give me? Somewhere around 13 or 14? I should turn that on first. 132 divided by 9.81 gives me 13.5. So that means that the force of gravity would be 13.5 times bigger by changing the radius to the radius of the moon. Or we could say the ratio, if you wanted to express it that way, the ratio would be 13 to 1. So however you want to express that as a comparison is fine. 13 times bigger, 13 to 1, both of those work. Anybody get some of that? Yes? How many people actually thought of dividing? How many people were thinking more like subtracting or okay. Like I say, subtracting is a way of comparing, right? But the best way to compare is divide. And whenever you get to Physics 30 and you write a diploma exam, and whenever you see a question where they want you to compare two numbers or find a ratio, then they expect you to use the best way, and that is divide.